Okay, so good morning here. Going to get started. Apologies for the delay. There's a bit of an issue with one of our reporters. This morning I thought I'd start with a retrospective as we did yesterday, and then go on to talk about some of the textured issues which come into play when thinking about the trade-off between the multiple types of modeling supported by any logic, bearing in mind that we're not choosing here an either-or situation where we can only model it one or the other, but where really we're trying to articulate areas of our model or characteristics of components of our model that that make them best suitable for one of these types of modeling or another. So with respect to the retrospective, yesterday we had a variety of materials that were presented or otherwise came up through the course of the day. We began with a look at a set of examples which highlighted AnyLogic's capacity to represent open populations, where we had agents come into being, be deleted from the population, and we saw that events, whether in their static, so-called static or dynamic form, 4 names I think, could be used to capture many of these features. So who can remember, where do we first see an event, an explicit event object introduced into our model yesterday? Sorry? Yeah, I heard someone say immigration, right. So we had people coming in once per day coming into the model. And I emphasize that events, AnyLogic's entire edifice rests atop handling of events. That's how it works. It goes from event to event to event and handles each of them. And it bears in mind noting that, as we'll discuss in the performance section later in the week, events have a disproportionate impact on performance. They shape the performance of the entire model, how many events are occurring. And events are ubiquitous throughout the AnyLogic infrastructure. So we saw that event object, which would periodically schedule events, although not in a fixed period, but with a period dictated by a rate. Thus, their inter-arrival time was exponentially distributed for the mean time of 1 day. I argued that there were events throughout AnyLogic. What are some other situations where events are handled within AnyLogic? I mentioned a number of them sort of in passing. What are sort of incidents that AnyLogic has to handle? It needs to do something when something happens. Agents communicate via messages, for example. There's events associated with that, sending that message, receiving that message. Okay, so that's good. How about other situations where events occur? The events associated with an agent's dynamics, transitions and state charts. So another great example. There are events for when the model starts up. The startup event. You can put some code there and it'll execute when the model starts up. When a particular agent comes into existence, you can put some code there so that when the agent comes into existence, it can squirrel away information on the agent's characteristics into the database or print out the joyous event of this agent coming into existence, or similarly when an agent is about to disappear, or the model is about to be stopped. Those are all sort of associated events. And AnyLogic provides you a variety of additional events as well. For example, if you want, by default, we have a sort of continuous time here, continuous time abstraction. So we have events occurring however frequently they need to occur. So maybe you have some parts of your model which on an occasional basis need to occur really quickly. Like you have a power outage and you're interested in capturing the vagaries of the brownout behavior in the city and the response to that. And then you have long periods of stasis, perhaps, where events only occur infrequently. You'll find that in some other sorts of modeling, everything is dictated by a lockstep. And indeed, many agent-based packages, Repass to pick an example, and NetLogo, others, you'll find that it's assumed that you have some sort of lockstep progression from one time step to the next, where the time between those time steps is assumed to be sort of fixed. So you have a set of regular time steps, and that's an issue if you have this kind of multi-scale behavior where sometimes there's a bunch going on, sort of a punctuated equilibrium to draw on, some terminology from paleontology, where you have a bunch of actions taking place in a burst, and then you have only these irregular actions. That can be an issue because you're forced by the least common denominator to sort of deal with things on a very frequent basis, so you can capture these events. So I did work in for the national government of a country in Southeast Asia, doing modeling of their infrastructure system, and they were concerned about tail risk, very concerned about tail risk with these sort of events. This is before any logic was, it was just back in the Cosmic Guide, but at that time it was more like a moat in the Cosmic Guide. It was in its formative years. And so we were using a package which forced us to simulate very, very fine time steps on the order of hours in a model where a lot of it was simulating economic changes in the economy. So you put a huge amount of effort in at a very fine time scale for many runs. And then some runs, the action happened. You had to simulate things. So these events are going on every time, throughout the model, and AnyLogic allows you to, in a very flexible way, have these events occurring however frequently they have to occur, and it bounces from one to the next, to the next, to the next. And there's actually a lot of events that end up getting scheduled, but end up being preempted by other events. For example, the agent's anticipated occurrence of end-stage renal disease is scheduled, but the agent dies first. And that event is unscheduled. So beneath the surface in AnyLogic is an event scheduler that runs from event to event to event. And some of those, when you run an AnyLogic model, some of those mysterious things down at the bottom that have numbers flashing or incrementing or what have you, or changing, have to do with how many events per second AnyLogic is handling, sort of how many events it's handling, and that's commonly in hundreds of thousands, for example, potentially more if you have multiple cores, you're running multiple simulations at the same time or what have you. So you have this event-driven infrastructure here, and events are core to AnyLogic. Yesterday we saw how we can explicitly reify a type of event that we put into the model as an object and specify its schedule. One-time basis on a rate, in other words, this hazard, this exponential redistributed time between events on a one-time basis when some condition occurs, having the eventifier, etc. Very powerful. I kind of muttered some things about dynamic events, which are very, very useful when you want to schedule an event on a one-time basis, some amount of time in the future. You kind of wrap up all information that will be needed for that event now, so that when it occurs, it knows what to do. So you schedule the birth of a deer, I don't know how many months ahead of time. Maria? How long is gestation for a deer? 5 months. Okay, so you schedule. So at the time of conception, you record away the information on who the dad is, and you record where it occurred, and you record the health status of the parents, maybe some aspects of their genetics or whatever, and all that information is wrapped up with this impending birth, and 5 months later, boom, the deer is born into existence, and it knows who not only its mom is, but who its dad is as well, and where it was conceived, all that sort of stuff. So in terms of dynamic events are really useful too. So we talked about events yesterday as a tool, reified as an object, but bear in mind that there are these events occurring all throughout AnyLogic, And it's no distortion to say that any logic is built atop a foundation of event handling, of event scheduling and handling. And it's its great strength that it can do this in continuous time with the level of detail required. So we built up this population model with, and I was doing this a lot of ad lib, and I apologize if it got confusing, but we started seeing, for example, by request from the audience, I got a bunch of requests dynamically during the night, weave them in. Things like, suppose we wanted an agent to be able to remember their children, or suppose we wanted them to be able to keep track of their mother, that sort of information. We saw how those could be readily done. How do we keep track of children? I wanted to fit that in. I didn't have any other place I'm anticipating for sure getting that into the boot camp, so I wanted you to see it. How do we do that? What do we introduce it to? And where do we introduce it? It's a collection. And where was it introduced? Was it introduced in Maine, or in the experiment, or in a person? So each person kept track of their own children. And when a birth occurred, we did what? We added it into the collection. Yeah. And we also saw something kind of interesting there, which Carmel had asked about, and there was some sort of mixed signals any logic gives about it. Once a person is deleted from the population, they disappear visually. They're no longer obvious or removed from that population. And they seem in any way, in lots of ways, gone. But it turns out that we can still gain access to them. As long as there's some references to that person, that information will stick around. So for example, if a person's mother has passed away, they're removed from the population, but we can still gain access to their information. They're still there as a person, they're just no longer part of the population. If we eliminated all references to them, they could be cleaned up and disappear. This is basically what's called garbage collection. So we saw that we could actually record intergenerational information, for example, between agents. And when agents disappeared, when agents were in the population, suppose you had a reference to your mother and she was still in the population, it would say something like the name of the population, her name would be the name of the population and the index into the population. So population number 7, something like that. When she disappeared from the population, how did that change? That became what? Population number -1. But she was still there. She was still around. And there was still information about her that could be elicited. So we actually saw that as part of this as well. So in any case, this dynamic model with open populations exhibited how we could capture many vital processes such as birth, such as death, some mortality. We had some fixed rate. It could be time varying or age varying. And we also saw how we could have immigration as part of that. We did see a birth process represented in sort of a simplistic form, and we saw how agents could moreover be added into each other's networks, which highlighted the capacity to represent dynamic networks in any logic. Some of you are from an infectious disease background, probably have interest in capturing assortivity among agents. And we saw yesterday, after this initial presentation, I went through sort of a whirlwind tour of different networks in any logic and different layouts which you use to display those networks, or generally to distribute people in space. So we saw that we could specify network types. Give me some of the network types that we saw. Okay, distance based. That's great. So that was actually the very first we saw. Oldie but goodie. And what were some others? A random network, a Poisson random network, Erdos random network, Bernoulli network. It goes by different names, but it's characterized by global structure, by sort of a wanton disregard for locality. Two people are connected with a certain probability, regardless of who their other friends are. There's just sort of promiscuous pairing across this entire network. So there's another one. How about some others? Small world, good. That was characterized by a mixture between that sort of global type of network structure we see in random and another network which is highly localized. The most localized in a sort of one-dimensional sense that you can imagine. What is that? Ring lattice. People are just connected with sort of neighbors and successive and ultimately forms a big ring. Sort of a one-dimensional form of locality in contrast to the two-dimensional form that you see with distance-based network. And finally, there's another network, very common network type that has a lot of theoretical interest for the past 15 or so years, and that is scale-free network, where there's huge heterogeneity in numbers of connections that individuals have, and the distribution for the number of connections associated with individuals follows the power law distribution. So if you take the log plot of it, it's a straight line. So there's some people, this is a log axis, and there's some small number of people out there in the population who have huge numbers of connections. And sometimes you get the tail wagging the dog. Frequently you do. These tails dominate. The heterogeneity dominates. Sometimes you get these people, for example, with an infectious disease, these people are important, huge numbers of connections, both because they are more likely to get infected. They have lots and lots of connections, become magnets for infection, but also because if infected, they're more likely to transmit it. Because they have lots of connections to disseminate it. So they become the hubs in the network, cores of the network. They can spread it out to other people. So they can have a very disproportionate impact. And in fact, if you look at classical mathematical epidemiology, you can often accommodate a certain amount of variability in our networks by looking at corrections for the contact rate, but with a scale-free network that breaks down because there's just so much heterogeneity, and the ones with large numbers of connections dominate so heavily. So that theory is sort of how to correct for it, how to correct the contact rate such that we can sort of simulate it in an aggregate way. Breaks out. This is sort of easy. This is sigma squared over mu. So this is sort of a correction factor you can put out. And normally, but with a scale-free network that breaks down effectively. Okay, so we saw those sort of networks, and then we have several layout types, which arrange people in different forms in terms of their spatial location in any logic. We saw that there are two types of spaces in any logic: continuous and discrete. And the continuous space, which is what we've been using for the most part, we've seen people can be arranged in various forms. What's one of the layouts that we've used a lot? It's a what layout? It's a random layout, sort of scattered around. Each person is independent of the others and scattered around. But there are several other types of layouts as well. One is an arranged layout. This is the very first one we saw. Remember that model we started with where the infection was spreading, we saw waves of infection? Those people's layout was not independent of one another. They were arranged in a grid, regular grid. And this is how it's done. You could have gone to that model and checked out the environment, and you would have seen a layout type of arranged. So we could put people in a regular grid. What was another type of layout that was particularly nice for depicting the ring lattice network? A ring layout. But this was also useful for depicting other sorts of networks. For example, those that had the occasional long-term distance connection in addition to ones that are predominantly local. A weighted combination of local and global that we call a what sort of network? What sort of network is a mixture of two other sorts? Small world. Small world. So if we had a small world network, we could kind of depict it with a ring lattice, a ring layout, and we kind of see the mostly local structure and some global connections. Okay, so we saw a bunch of different types of layouts, and those aren't all of them. It's not exhaustive. But that clued us into sort of types of layouts. There are two types of situations where networks and layout, spatial location. I don't careful this word layout. I think it should be spatial position or something like that. It's more than just appearance. It has to do with where people are located. There's two situations where these two are interacting. One of them was a distance-based network where people's connectivity, their topology, who is connected to whom, depends on their position. Two people are connected if and only if they lie within a certain distance of one another. Conversely, there's a situation where we have a spring mass layout, which depends on the network structure. Personally, I find any logic spring mass algorithm singularly crude and unworthy. And I think they could invest a lot in some of the better algorithms that are found in, for example, in the GEFI package, or even GAS network visualization packages. I think Hayek also has some decent ones. And I'll try to push on any logics team over in St. Petersburg to incorporate better layout algorithms, because they can do a lot for a modest amount of work. If they want, I can have a student here write a code for them to use. But fundamentally, the layouts need to be improved so that we can nicely visualize complex networks in any logic. Right now, the spring mass layout is kind of an attempt to that, but it tends to be kind of messy, even for modest-sized networks. And there's a lot better things you could do. Anyway, those were some things with layout, with spatial position, and topology. Who's connected with whom? Where are those things dictated, ladies and gentlemen? Where do we go in the model to set characteristics of where people are located and to whom they're connected? In other words, the network type and the layout type. Where do we set that? The environment. Now, ladies and gentlemen, it's extremely important, from my perspective, to take greatest advantage of any logic. It's extremely important that you think flexibly. Any logic has struck me as having one of its foremost strengths is its flexibility, is its profound flexibility in terms of reconfiguring things. One of its less strong components is that you'll often won't be aware of the generality that's there. So there's some just amazing features that lay buried, and I'm trying to sort of point you to them to some degree in the boot camp, but I can't do it exhaustively. One of the nice things you got to realize is don't get stuck. Please try to make efforts to avoid getting stuck in a boilerplate sort of mode where you think, oh, okay, state charts are used at an individual level, and that's the only way of describing behavior at the individual level. They can only be used at the individual level. And environments only live in Maine, and populations only live in Maine. Don't get stuck in that mode of thinking. Question your assumptions. Question your premises in these regards. Lock your doors and check your premises. You need to realize that any logic's mechanisms are extremely general, and some of the ugly things you saw, like that rude awareness of a thing called active object, what that actually is achieving is a profound generality of what you can do in terms of configuring things. So, for example, you could put environments in person. You could have populations as part of persons. There's this hierarchical model that is part of the example models I give you, where you'll find a YouTube video of me explaining that how it's built up step by step. And there, you have populations living within agents and subpopulations of other agents, so you have people, cities, and a region, and you can reconfigure things there. You can have state charts in your main class if you want. You can have stocks and flows, continuous dynamics at the level of an agent or in the main population. You can reconfigure these things in any number of different ways that you want. So it's kind of like not buying a set of Legos and looking just what's shown on the box cover and just building that. With these Legos, you can do an awful lot of stuff. You can reconfigure them to your heart's delight, and it's important to take best advantage of any logic that you use your imagination and say, I wonder if I can do this. Occasionally you'll get an answer of no, but an incredible amount of the time the answer will be yes. You can actually do this. And I've been struck by the number of times I thought, you can't do this, but turns out you can. An example we talked about yesterday, for example, was having persons have a population within them that also holds persons or something like that. And all too often, we assume things are not possible, and in fact they are. Okay, so from sort of the lectures yesterday, we then got a talk midday. Yes. Yeah.
Well, you were talking about the environment,
Yeah.
and then we talked before about the type of network.
Yes.
And then you have the idea that, let's say, depending on the type of network, you have the degree of the network, number of connections, the distribution of number of
Yep.
connections.
Yep.
Now, here in any logic, you have a number that is called connection per agent.
Yeah.
Wouldn't it be that the number of connections? What that number is really?
Okay, so that's a good question. There is a connections per agent formula there. So Scott, maybe you could quickly check for me, or one of the other TAs quickly check for me. Is connections per agent a field that has to be constant, or can that actually be an expression?
I'm pretty sure it can be an expression.
Yeah. This is one of the areas where you got to question your assumptions, because I've used it as an expression for the vast majority of models I've built, certainly, but I don't know if that's enforced. So
The question is whether or not it's dynamic.
That's correct. Right, exactly.
That should probably be under the.
But dynamic means different property to these people than it does to a computer scientist. So you got to be very careful about that.
Distributed networks.
Yeah. Yeah. So the answer is for different types of networks, and this is a little bit confusing in the anti-logic interface, you'll see different properties made specifiable, that you can specify. Okay. And that connections per agent property is specified for certain networks and not for others. For example, connections per agent is specified most notably for a random network, also for a small world network, because it contains a component, it's a weighted combination of a random network. It's not specified, for example, for a scale-free network. Okay? For a scale-free network, that's built up using an algorithm, first described by Barabasi and Albert in Science magazine, and the scale-free network, you don't explicitly specify the connections per agent. That's an emergent property of this phenomena, building up this network from scratch using preferential attachment, attaching new connections based on how many connections people already have, and favoring those who already have connections. So that, yes.
The random network
Yeah.
is the average number.
Yeah. So it's not you can't specify an expression.
But
You
that's
can.
Computer
it's
science
average,
terms, it's
but-
not a dynamically specified.
right. Well, that's a confusing part.
Yeah.
Because actually you can include there a type of distribution variable. So you can say constant, and then you can specify the parameters. And for me, that kind of comes from the type of network. And how could I specify? Maybe this is too kind of detailed question.
Well, okay. So you are saying you can in fact specify an expression then in any logic?
Well, at least I can see it, but I don't know.
Okay. So what that would mean is that for each successive agent in a random network, it's going to be, I suppose, drawing the number of connections that that agent will have. Now, how it could achieve that, you see, networks are, so there's a generative component here. Networks are built up over time, okay? We have to figure out who's connected with whom. And there's certain constraints, logical constraints on how many connections a person can have that depend on other people. You can't have, for example, you can't have a network where one person in the entire population has a number of connections equal to everyone in the rest of the population, and then everyone else has exactly 0 connections or something like that. It doesn't make logical sense. It has to balance out in some way. So I'd be a bit surprised if you could impose a distribution there. I think it's something that's built up when you build a network, and that what that I think specifies is a mean number of connections that it's trying to achieve for a given person. But a given person will exhibit variability. The number of connections for a given person in that population that achieves that mean of, say, 10, there ought to be a distribution on a per-person basis that's reflected the fact that some people, by the luck of the draw, happen to get more connected to more people than others. Because the process of building a Poisson random network basically is a matter of, for each pair of connections, you have a certain probability of being connected. And so it's going to probably be drawing pairs of connections randomly and connecting those people up. And by luck of the draw, some people may get more connections and other people will get less. That's an emergent property of the network building, as I think you expressed that, which is quite right. And that's why I don't think you can just impose a distribution.
What I see is you can impose that only in the random network.
Okay.
But in the other one, for example, if you have 3, you cannot do anything.
Okay, well,
it's very out.
okay, let's.
So that's the kind of.
Let me show asking questions about this, David, and I admire your persistence on this point. And no, and I think what I should really do is I owe it to the balance of the people and to yourself to go and actually say how I would investigate this. So I hear this, and what David's talking about, we're talking about things which you and I visualize in our head, but the others have probably, they're somewhat innocent of these issues. So if we were to go in Maine and go to the environment, you notice we can pick a network type and a layout type. This is what we were talking about. And what I was saying before, let's double click this. I like to teach life skills to my students. So here's a depiction. You double click on it, it becomes full screen, so you can see it in its fulsomeness. And so you go to distance based and you have connection range, for example, 50. You go to a random network and you have connections per agent of that. You go to a ring lattice network and you also have connections per agent. And you go to a small world network and you have some combination. By the way, go see my lecture. If you go see my lecture slides on this that I've provided to you, I warn you that some of these parameters are inconsistent with others, how they're specified. In one case, I think it's connections per agent, and maybe for random and ring lattice, they're actually off from each other in their meaning by a factor of 2 or something like that, in terms of how they're specified by any logic. In other words, I think this connections, in one case, it's only counting connections on one side or something like that. I don't remember the details, but you can find the details in my slides to be careful about what these mean. But the point is, what David's asking about is, you notice for different of these networks, different fields are enabled here. You can change different things for different networks. So for example, a scale-free network defines this parameter m, which is under-documented in any logic, but has to do with approximately twice the number of hubs in the network. Something along those lines, also in my notes. Small world network, there you can specify connections per agents, and this fraction of times those connections are local in character. This again is a sort of weighted combination of 2 types of networks, and this specifies how much of it is just a purely local ring lattice. So what David, what you're asking about is, what does this parameter do, right?
Because it affects a lot of behavior of your
Sure.
Sure, so could I impose a log normal distribution on here? And I'm gonna say this is log normally distributed with a log mean of 2 and a log standard deviation of 2 and a minimum value of 0, something like that. And could I compile this? What's gonna happen when any logic compiles this? So I'm gonna build, and I'm gonna see if bad things happen. And it says build completed successfully. Any logic is happy. Now, I think you're fooling yourself. I think it's allowing you to fool yourself in a crude, in a fashion that's objectionable. So let's go see where this code is used. How do I go see where this code is used? I go to this place and I press Control J. And now I'm placed where this code is used. And I see exactly my suspicions were fully borne out, folks. Hoodwinked by the interface. So what's happening here is that it's calling and saying, go set up a random network. Go set up a random network with these properties. It's saying, establish a random network in this population. And what is the number of connections that for this random network that are specified? It's a draw from log normal. In other words, you are basically saying here, without realizing it, what you're saying exactly to any logic is, create for me a Poisson random network where the mean number of connections for the entire network is drawn from this distribution. In other words, I'll roll the dice and you go build a network with the number of connections per agent as dictated by that dice I roll. What this is not saying, is not enforcing, is the distribution on a per person basis being drawn from this. It's just saying that the mean to which to aspire in building that network is dictated by this value. Okay? That's what's going on. How do I know that? Well, first of all, I figured logically it has to be the case. I just don't see any way, because you're building up this network in a generative fashion. You're constructing it with, and you can't just impose magically some distribution for people in the network, because it won't balance out necessarily. There's a sort of set of constraints mathematically that have to be the case in place for the network to be balanced. Again, if I'm in a two-person network, if I'm in a network with Kurt, I can't, it's not a needle sharing network, by the way. I can't have a connection and he not have a connection. It doesn't make sense. So there has to be sort of some balance in the network. And if you allowed an arbitrary distribution on people's connection, number of connections, you wouldn't be able to necessarily achieve that constraint. So here, just looking at this, what's clearly happening is you're telling, hey, environment, go off and build me a network, and this is the value for it. And this is a value. In Java, you're passing a specific value. It draws this value from this log normal distribution, and it gets a value of 10. And it goes off and builds a network with a mean number of connections per person of 10. In another case, it may draw the value of 1 from this. And it goes off and builds a network with a mean number of connections per person of 1. Those are two very different networks, and it's not, I think, what you're trying to achieve. Does that make sense? Yeah.
But that's also true because it's not a directional network. If you had a directed network, then you could actually do what you're talking about.
Yeah.
Not in
That's
logic,
correct.
but in logic.
Exactly. Yeah, it's a very good point. And ladies and gentlemen, any logic 7 supports directional network.
Oh yes, oh my god, yes.
Yeah. So you can have, this person is my mother, and I'm not her mother, right? Which is a good thing for certain types of semantics. So anyway, this is a case where you have to be careful about what it means. Now, how would you know this? How would you know this? Well, one thing is you could experiment. If you feel comfortable looking at this, or have someone that you could bring in to look at it, you can do that. But normally this is not what I do. Another thing is, so you could build some simple examples and you can see, okay, yeah, this is what it's doing. Another thing is you could ask any logic support and they'll tell it to you immediately. But yeah, this is a case where you could be fooled by that expression. Okay. Does that help? Okay. But the other thing I wanted to highlight here, and I know I'm going on a bit about this, but these retrospectives I think are helpful for synthesizing some things. So the other thing that occurred yesterday was this guest lecture. And as I said yesterday, I thought the guest lecture did an admirable
job of sort of highlighting some of the issues, even philosophical issues, and certainly practical issues that apply in the modeling process. And I specifically wanted to highlight the issue of emergence, and note the fact that sort of the special place that this ends up playing within within the sort of agent-based modeling milieu. So there's an article by Josh Epstein, and I'll see if I can send you the reference to it, called "The Foundations of Generative Social Science," or of generative approaches in social science, something along those lines. He actually has several variants of this article, but Epstein has written at a level philosophically about this that I haven't seen others write on, and he talks about the importance of distinguishing between models where we try to build in behavior or patterns that we see directly into the model. So we have empirical data and we put that into the model and simulate from it, versus models where we try to explain that data from underlying factors. And he argues that in agent-based modeling, it's the capacity to generate as emergent properties many of the patterns we see in the world that gives it its power to ask counterfactual questions. Its generality to be taken to different, translated to different contexts. If we can explain where this pattern is coming from, we have a better chance of being able to translate this model into a different context, because we're capturing the basic mechanisms that underlie and can explain these patterns in a particular context. At the same time, this is a highly practical trade-off, because often putting in the theory that explains these patterns requires a lot of work. So Gregor right now, for example, is trying to work on, essentially what the underlying theory is of herd formation on the part of individual animal sort of psychology. What rules do they use as to who to hang around? And this is hard. Now, if it can be achieved, the model has extra level of generality, but there is a real question of at what point you sort of say, okay, for the sake of this model, we'll build these patterns in, and later we'll go and explicate it further. So the example came up, for example, sleep, and to what degree do you sort of say, okay, an animal spends 30% of its time sleeping, and to what degree is that something which emerges from the confluence of all these different pressures on the animal to go mate, to go find water, to go find food, the pressure of fatigue, the pressure of wanting to take care of the fawn that's with it, or what have you. To what degree is that 30% something that we want the model to match, sort of as a result of its mechanisms? We want it to have emergent behavior which matches that 30%. And to what degree do we just impose that as an exogenous factor? And this fundamentally is a practical issue that has to do with the purpose of your model and to what degree it will be important to secure generality on it, to what degree you're going to examine interventions which may affect some of those underlying factors. So, for example, if part of what's shaping that 30% is the fact that you have to go forage for food sources in an aggressive fashion, potentially some intervention that changed the availability of grain, to the animals might nudge that somewhat, or something which fenced animals into a smaller area might end up affecting something like that. And if we just program that number in directly and post that on our model, we might miss the fact that our intervention changes this sort of situation in a way that would radically shift this division of time. I'm not picking a great example, but you see this in model after model after model. Another example would be contact rates in infectious disease transmission. How often do people contact people of their own type, of a different sort, that sort of thing?
what are the contact rates and what's the contact matrix. We can describe people's contact patterns in a contact matrix as using a contact matrix that this sort of person, say we divide the population into 3 categories, and these sort of people mix with each other to a certain degree. This is sort of, group A mixing with group A, group A mixing with group B, group B mixing with group B here, group C mixing with group C here. But this is, A mixing with B and B mixing with C here, etc. Okay? So we can summarize contact patterns using this, and we can impose this on our model. A certain fraction of the time, A's mix with A's versus A's mix with B's versus A's mix with C. We can impose that on our model. And that's great. It's probably an adequate description. It's an adequate description of the current situation. But what would happen if there's some change in place, maybe just some secular change over time, or some change as a result of an intervention that leads the number of C's to be drastically reduced? Would A's really still be spending 30% of their time with C's after that? If there are far, far fewer C's around, maybe just one C person around, would A's really go out of their way to spend 30% of their time as originally with this C, if you had that drastic reduction in the number of C's? Well, kind of stretching it to believe that these numbers will remain the same even with big changes here in the numbers of people. And sometimes our interventions may change these numbers of people a lot. So, maybe these are sexual risk categories: high risk, medium risk, and low risk, and or say low, medium, and high, and we undertake an intervention in terms of an awareness campaign, or maybe it's a safe sex, sort of classroom exercise, or maybe it's something having to do with risk perception to shape people's awareness of risks out there. Or maybe there's just, because the epidemic is going along, people with high-risk behavior realize they've got to be more cautious, and there's fewer and fewer high-risk people. Would it really still be the case that low-risk people are circulating within the same amount of time? That's kind of hard to believe at a certain point. If we impose this matrix, we may capture the current situation, but we're not going to be able to capture counterfactuals as well. Situations where we have an intervention in place that we haven't actually observed right now. So we might go instead to a matrix where we have a formulation of sort of preferences that people have to mix with each other. So, A's on a per person basis, an A would rather spend time with an A, but they're also, if there's lots of B's around, they're willing to interact with B's. Their preference would just be half the level it is to mix with another A. And similarly, to mix with a C, it's maybe, who knows, a fraction of that yet, 0.1. So here we have sort of preferences, how much would A's prefer to be around A's, B's, or C's? And this will get you further than this matrix. This matrix is sort of describing the current mixing, but it presupposes it. It builds into it. It hard codes in a way the vagaries of how many people there are in each of these categories. This is capturing preferences, which is more robust to kind of, if there's fewer of these people around, then that just means A's time will be more devoted to A's and B's. Okay, so here encoding preferences is more robust to changes in the sort of balance of the population groups in terms of how many people are in different population groups, and that's good. But there may be some things that are not captured here. For example, these numbers on preferences might be obscuring certain practicalities of the situation, like how people travel to work, whether they travel in a car, whether they travel in a public transit system, or whatever. It might presuppose that kids are still going to school and that, that there's opportunities for mixing in malls or other sort of public forums, and that, transit stations are still operating. In the event of some sort of, pandemic or something, you might have schools closing down. You might have perhaps people's use of public transit changing rapidly. And these preferences might not be actionable in the same way. So, another thing you might do to bring it down to an even, deeper level, you might ask, for example, and apologies for sort of mixing metaphors here, but you might look at how are these contact patterns driven by mobility patterns, or, or sort of there's a word for this, I'm drawing a blank on, sort of co-location, sharing of spaces in the same place. So maybe these interactions A would have with C will now be longer distance interactions via information technologies or chatting, remotely without actually being co-located. So we might look at mobility patterns as kind of driving the ability to actualize preferences, as driving contact patterns, and then we might ask how do interventions affect mobility patterns, for example. To what degree, if we intervene in the system, might we change how people move around, and therefore how many people are brought into contact in the context of a bus, or brought into contact in the context of a bus station, brought into contact, in office spaces. So if we were to dictate schools will shut down, if we were to say request that employers, during the peak of the pandemic, request telecommuting and so on, maybe that would end up drastically shifting these patterns in a way that would change how much fraction of time people spend together, and therefore affects contact rates. Representing things at this level in the model will take a lot more work. This itself took more work. This took more work yet, but it gives you that requisite flexibility to capture these counterfactuals in a way that's richer. But ultimately, ladies and gentlemen, modeling is a practical endeavor. It's an endeavor where you're balancing, the desired generality of the model on the one hand against the availability of time, data resources, expertise in terms of programming and all those sorts of things, and team size, etc. So it may be that you want to use this sort of model. You just have to be very conscious of what the trade-offs are, what the limitations are. What's the sphere of questions you can reliably address with this sort of model, and try to address things in that sphere. If you want to address things that would radically change the mobility patterns of people, then you're probably going to want a model that's more detailed. But you want to play to the field. You want to play your, you want to undertake model attributes that will speak to your research questions, and bear in mind that certain research questions will require more detail, certain will not impose that need for more detail. So you want to, drive to the conditions, sort of build the type of model that you need, not the sort of model you just reflexively fall into because this is the way things work in the world. And it's very important to make that a conscious, reflective decision, and not just one where you're trying to sort of mirror what you know is the case. You want that to relate to your scope, and it's good to sort of very clearly articulate, where we're comfortable things falling within these three categories. So endogenously produced, or produces its emergent behavior from the anthropological interacting parts, exogenous versus ignored, or the exogenous is imposed. Is that helpful in talking about some of those factors?
Can I ask you a question?
Sure.
That matrix.
Yeah.
Assumes, particularly there's another factor that plays an important role. That the matrix assumes the universal susceptibility. So if you have mixing various parts, you will have an outcome. Certain number of people will get an infection. They don't get. But even in this context, the mixing and networks are not
Yep.
So how can you also superimpose or run into diagrams
Right.
to reflect the intrinsic ability to get the information?
Sure. So that's a great question. And you're right, this is an abstraction which abstracts away from a lot of details. The good news is that this is just part of the picture on these different groups. Typically, we may have in place different mixing groups, but there'll also be other aspects of heterogeneity that you can capture. And the sorts of models that we've been talking about thus far, sort of agent-based models, are it's going to say uniquely poised, but they're certainly exquisitely poised. I would have to ponder unique for a few minutes. They're certainly exquisitely poised to capture other aspects of heterogeneity. So, for example, capture progression of comorbidities, as we stated. Imagine several state charts for a given individual, each capturing a different set of comorbidities. Or imagine a situation where you have similar ability to track at an individual level immune system strength in a way that would allow you to capture the buildup of immune memory on the part of an individual through activation of CTLs to fight an infection. You get memory cell production and you get persistence of immune memory. There are examples like this, in fact, that I've provided to you as part of the examples for this class. And if you're characterizing things in an individual-based model, you can capture those sort of phenomena at quite some level of specificity. There then becomes the question of how to capture them in a general way, because there's often multiple underlying conditions of interest. And you may have statistics on, for example, multiple comorbidities. Let's suppose taking immunosuppressants, let's suppose presence of end-stage renal disease, let's suppose alcoholism. You may have some sense about how those, from a relative risk perspective, impact the vulnerability to infection. But at some point, there's a question of to what degree do you deal with those as kind of solitudes or kind of just on an ad hoc basis, and to what degree, so HIV status would obviously be another one, to what degree do you want to actually put into each individual as is present for like the flu immunoappy model that I show you or the chlamydia one that we've also distributed, these sort of dynamics at the level of the immune system, get into sort of modeling immune dynamics and build up of memory cells and decay of memory cells over time, et cetera. So, here we might have immune memory built up, and we might distinguish that, in fact, into several stocks, with precursor cells and effector cells or what have you. And those will then mediate the ways in which infection occurs within the body or something like that. And HIV, end-stage renal disease, alcoholism might all be mediated by sort of immune system activity and strength of immune response to infection. And that might be a sort of a more general underlying mechanism to think about individual response to these diseases. And any logic as a framework is unparalleled in allowing you to capture this sort of multi-scale behavior with people, in networks getting infected through others, but also responding through their immune system activation in this way.
That means you can't put that in the DNA.
You can't. Well,
let's say the person A
yeah.
interacts with person B or person C, and
Yeah.
there's a certain probability of interaction occur.
Yeah.
If person A is susceptible and person
That's right.
B is immune, even though they no matter how close the interaction is going to be more infected.
That's right.
And then, yeah, because the person, for example, B could have an underlying immune deficiency and they're also susceptible to it.
Right.
If they interact, they not only get disease, but immune disease.
Indeed.
What I'm hearing is that it's possible to transpose this disease.
It is. It wouldn't be captured, to be clear. We wouldn't aspire to capture it in a mixing matrix so much as this is one abstraction of considerations for the model having to do with people's contact patterns, but we'd be capturing in other aspects of individual heterogeneity, potentially in a very, very rich fashion, or at the least in a way that we say represent common comorbidities for individuals and progression of those comorbidities. In a way that might impose relative risk of infections that are higher for, if you have acute stage HIV or whatever.
And a good example is the expression of the weighted factor.
Indeed.
And actually, there's a lot of data there.
Indeed. Exactly. Yeah, and this is an area of active work for us as a personal group. So we have studies going on looking precisely at the impact, for example, of smoking on development of active TB, field study going on, and work that we've done with diabetes and TB. And agent-based models are key to these investigations because of the capacity to gracefully represent these additional comorbidities. But they are something that is abstracted away from the mixing matrix, but are captured in a fundamental way, sort of elsewhere in the model, having to do with individual vulnerability to infection or to development of in the case of active TB, of active TB, or development of things like cavitary TB, a more serious form that can spread. So I hope that's good. Okay, so any questions on this issue? I know I'm taking time, but it seemed to me there were such good questions about it yesterday. I thought I would sort of try to address this point a little bit further this morning. Okay? Glad to talk about it. So it was a long retrospective, folks, and I have patience. So this would be.